Welcome to the Algebra 2 video for skill number 68. I can use the number e to write and graph and solve real-world exponential and natural logarithms. We have learned that the logarithm is the method by which we undo an exponential equation. Oftentimes what we have is a log with a base, so this would be log base 7 of 2. If the log is not written, so log of 100 we'll say, there is no base written, so we assume that base to be 10, and when we do that we call that a common logarithm. We have another special type of logarithm, and that's a logarithm with base e. So if we had log base e of 23 we'll say, then what we have is actually the natural logarithm. So the base of e gives us what's called a natural logarithm. And e is a very special number. It's approximately 2.718. The technical definition, or one technical definition, is, and you do not need to know this, but it's the limit as n approaches infinity of the value 1 plus 1 over n raised to the nth power. And I showed a couple substitute values, so we put 2 in and we get 2.25. When we bump it up to 10 we get 2.593. If we bump it up to 1,000 we get 2.7169. And the closer our value of n gets to infinity, the closer we get to the true value for e. It's an irrational number like pi. It goes on, the decimal goes on forever, non-terminating and non-repeating. So down here I wrote down a couple examples. The first is a common logarithm. So our base 10, we just, oops, that should say, that's a typo over there. That should say, let's fix that, log of 5. All right, and for our natural log, instead of writing log base e, what we will write instead is ln for logarithm naturel. So we can shorthand that. The natural log shares all the same properties as all other logarithms. So we have the product property, which says the natural log of a plus the natural log of b is equal to the natural log of a times b. The quotient property, which says if we're subtracting our two logs, we take the quotient of the two. And then finally the power property, which allows us to move our exponent down in front and get p times the natural log of a. On page 68b, we continue showing some examples of how the natural log gets applied, much in the same way where we had the principle log base b of b is equal to 1. Here we have the common logarithm, which says log base 10 of 10, or just log base 10 equals 1. We get the same thing if we are using the natural logarithm. So our natural logarithm log base e becomes natural log of e, and since our base matches our argument, it's equal to 1. In the next two examples, when you raise the logarithm as an exponent, just like when we took log base 10 and made it the exponent of a 10, those cancel out and we get a value of x. If we do the same thing for e, the e and the ln cancel out and we get a value of x. So what we have here is example 1, which says simplify the natural log of e to the negative 5x. And for that, our very first thing that we can do is we use the power property, which says move the exponent down in front. So we get negative 5x becomes what are multiplied by in front, and natural log of e is the other part of the product. We can simplify natural log of e to equal 1. So now we have negative 5x times 1, which is negative 5x. What we're demonstrating here is the power property and that the natural log of E equals 1. So this has two different properties being applied in the execution of the problem. Example 2 is going to use, example 2 we have e to the ln. Up here we have e to the ln, so those two cancel out and we're just left with what we are taking the log of, or rather the natural log of. One way that we use the value e is in compounded interest. So previously we learned about simple interest, and I gave you the formula for simple interest as a times 1 plus r to the t. We could take simple interest and expand it and say, well, let's, instead of compounding it annually, maybe we compound it twice a year. So a times 1 plus, we'll say our 5%, divided by twice per year, 2 times per year, and then the number of years, maybe 7 years. That means every 6 months we add an interest payment to the bank account. Compounded interest, where it's compounded continuously, uses this formula. Principal times e to the RT. So if I had $5,000 and it was compounded continuously at a 7% interest for 25 years, that is the equation I would use to evaluate what I have after 25 years. On page 68C, we look at an example of two different bank accounts. And in one bank account, I'm going to invest $2,500 at 6%, and the other one I'll do the same. The only difference is one of them is compounded biannually, so twice a year, and the other one is compounded continuously. And I want to see what the difference would be after 30 years. In the biannual calculation, I plug in the values that I know. A is our initial investment of $2,500. Our rate is 6%. The number of times it's compounded is twice a year, and the number of years is 30 years. After I plug all those values into the equation and simplify each step along the way, I find that my bank account has $14,729 after 30 years. If I go with a continuous compounding, my principal amount, which is pretty much the same thing as A, is $2,500. My rate is also 6%, and the time is 30 years. I plug those values in to my continuous compound formula, and I simplify the values and arrive at a total value of $15,124. As you can see, continuous compounding at the same interest rate yields slightly more money. Oftentimes you'll have an option of two different types of bank accounts, one that has continuous compounding and one that is simple interest, either annual or maybe it's monthly interest. And it's often a good idea to take a look at these two equations to find out how much you'll have after a certain number of years to decide which bank account is the best option for you. A second way that E is used is in calculating half-life or decay of substances. So let's take a look at an example there. The half-life of a substance is the time it takes for half of the substance to break down or convert to another substance. This natural decay can be modeled with the following function. N of t is equal to n sub 0 e to the negative k times t. N sub 0 represents the amount of your material at time 0. K is a decay constant, and different types of matter have different decay constants. We'll be working at finding the decay constant for some types of matter. T is the time, usually calculated in years, but sometimes we use different measures. And then N of t is the amount remaining after t years. On the next page we'll look at an example where first we find the decay constant and then we find out how much time it takes to have, I think, 15% left. All right, on page 68D we have two examples. We'll focus in on example 4 first, where we are looking to find the decay constant. So what we can do is, let's zoom in on this. Carbon-14 has a half-life of 5,730 years. What that means is, if you had 1 gram of carbon-14, after 5,730 years, we would wind up having half a gram of carbon-14. It would have decayed to some other type of matter. What we're being asked to do is find the decay constant, and if you remember, the decay constant is the K in the equation. So we take our equation, n of t equals n sub 0 e to the negative kt. At our time 0, we'll have 1 gram, we'll say, and after 5,730 years, we have half of that, so half a gram. And you'd find that if you put 1,000 grams down to 500 grams, or maybe 50 grams down to 25 grams, as long as you have half of it remaining, you'll wind up getting the same value when you're solving for K. So 0.5 equals 1 times e to the negative k times 5730. And what we're trying to do is solve for K. That's our end goal, solve for K. So in the first step, what I did was I simplified it. I got rid of the 1, because any number times 1 is 1 itself. And then in order to get rid of the e, I took the natural log of both sides. This relates back to the last skill where the tip was if you have an exponential expression on one side of the equation, which we do, the best plan of attack is to take the log of both sides. So I took the log of both sides, and since my base was e, I took the natural log of both sides. Once you do that, the natural log of e cancels out, so what we have is the power rule saying that negative 5730k times the natural log of e. And the natural log of e is equal to 1. So the right-hand side of the equation reduces to that. I divide both sides of the equation by negative 5730, and I arrive at a decay constant. So on the skill test, one particular skill you might be tested on is finding the decay constant. And things that might change is how many years or how long it takes for half-life to occur. Moving on to example 15, we take the problem a little bit further, and it says we have a sample of carbon-14 and we want to know how long until 15% of its original amount remains. So using what we've learned about carbon-14, it has a decay constant of 0.00012. We can plug that into our formula. So what we have here is a decay constant gets plugged in. We are starting with 1 gram, and we want to know when 15% of it is left. So how much time has passed to arrive at 15%? And from there, the calculation is very similar to what we did last time. We take the natural log of both sides, so natural log of 0.15 equals the natural log of e to the negative 0.00012t, and we apply the power rule, 12t times the natural log of e, which cancels itself out. And that's how we arrived at this point. Divide both sides by negative 0.0012, and we find that after nearly 16,000 years, so 15,809 years, our original gram has decayed to 15% of that. Or you could say if for every 100 grams we decayed down to only 15 grams of carbon-14. This problem here more closely resembles what you would probably be asked on a skill test. I may choose to give you the decay constant. I may ask that you find the decay constant first, which means example 4 and example 5 would be a singular problem. All right, for skill 68, a few things that we should be able to do is we should be able to simplify natural log expressions that have the value e in it, and we should understand how to use the value e. Most commonly we'll see it in compounded continuously equations where we have like p of t equals our principal times e to our rate over time, rate times time. Another way that we use this formula, or the value e, is in Halflife, and sub-zero e to the negative k of t. And we should be able to evaluate for k or evaluate for t, depending on the context of the problem. All right, this concludes the video for Skill 68.